Okay, let me have your attention, please, everybody. Let's please settle down to continue. Everyone, please. Let's go on. Continue. All right. So, what did we do last time? I would say views of art law. My goal today is to touch on Ampere and then finish these two chapters, or finish this chapter and then start Faraday. Probably not today, Faraday, but next time. Yeah.
Will the Faraday chapter be on the quiz too, or just the?
No. So let's please continue with this. So views of art law. So we did the following. We did this. Or we said the law states B is equal to B naught I over 4 pi ds cross r hat over r squared over mu naught I, or another way to state it, mu naught r I over 4 pi ds cross r over r cubed. Okay? And what do all these mean? It means this. We said if you have a current, let's say the current is going like this. This is current I, and you're interested in finding the magnetic field at a certain point. All right. So let's say I would like to find the magnetic field here at this point P. Okay. How do I find the magnetic field at this point P? I need to slice the wire into many little pieces, and each piece will have a length ds. ds is, let's say I take this segment here, this is ds. I will draw a vector that points from ps to the point P. So here is the vector that points from ps to point P, that's r. So that's the meaning of ds, that's the meaning of r. Okay. Then what we did, we applied this law to find the magnetic field due to an infinitely long current carrying wire, straight current carrying wire. So when we applied it to this, I'm going to just, for an infinite wire, we applied it. We said, suppose this is the wire. The current is I, and let's say we're at a distance A above, distance A, and we want to know the magnetic field at this point, at that dot. So how do we find that? You slice again the wire into many little pieces. So here is your little ds, and your ds's, they would start at minus infinity and they would end at infinity. And then r is the vector pointing from ds to this point. When we did this, we found the following. We found that the magnetic field had a magnitude of mu naught I over 2 pi a, where a is the distance from the wire. So this equation is applicable to an infinite line. Okay. The direction of the magnetic field
Towards us.
would be, above the wire would be towards you, below the wire it would be into the board. And we said, how do we find the direction? Yeah, your thumb would be what direction? The current, right? Your thumb is the current, and the magnetic field would be the direction of your fingers as they twirl around you. So the current is this way, so the magnetic field will be coming out, and then it will be going. Okay? So let me just redraw the wire by itself. So if the current is this way, then the magnetic field above the wire will be coming out, and below the wire it will be going in, like so. Next, I'm going to ask you a qualitative question, and then we'll do the force between two current carrying wires, and then we'll do a current loop, and then we'll go to amperes. So here is a question. Let's say I have a current wire, a wire carrying current, and the current is I. Okay. The current is to the right. Current is to the right. And let's say I have a charge here. Here is a positive charge. Q, a charge Q. And let's say the charge Q is at rest. If the charge Q is at rest, what's the magnetic force of this charge? 0. Because magnetic force is QV cross B, right? QV cross B. Magnetic force is QV cross B. So if it's not moving, there is no force, no magnetic force. Now let's say it's moving, and it will be moving parallel to the wire. Let's say the charge is now going to be moving in this direction. Okay. And now the question becomes, what's the direction of the force? And just to give direction, let's say this is I hat and this is J. Okay, so we need to state the force in terms of either I hat, J hat, or K hat. The force is QV cross with B, right? QV cross B. Are V and B perpendicular to each other?
Yeah. V and B. Yeah.
Yeah, V and B. Yeah. B is to the right. I'm sorry, V is to the right, and the magnetic field is
Towards us.
towards you. Okay, good. So the magnetic field is out of the board, the velocity is to the right. So they make a 90-degree angle with each other. So the magnitude of the cross product is just the product of all the magnitudes, right? So the cross product is just the product of all the magnitudes. Because cross products, they go with sine. So sine of 90, which is 1. So the force is going to just be QVB. But in what direction?
Downward.
Downwards. Yes, that's correct. The force is going to be in the downwards direction. So we would have to learn how to use our right hand to figure out the direction of the cross product. And so the magnetic field again is coming out. The velocity is this way. You need to curl your fingers from B to B. B towards B. B is to the right. So there are many ways to orient your fingers to the right. Like all these directions, it's to the right. But I need to curl my fingers to B. If I do this, B is not this way. So I need to do this, curl my fingers toward B because B is coming out. In what direction is my thumb?
Down.
Down. That's the direction of the force. So the force would be this way. Yes, and I heard negative J hat. Minus J hat direction. So that's the direction of the force. So the charge would be attracted. Right? The charge would be attracted to the wire. If it goes parallel. Yeah.
So, for us to know that the current, the direction of the magnetic field is into the page, we use like the current is going this way, so we're holding our wire.
Yeah.
So, what determines the magnetic field is the wire that is getting high. Right?
Correct. Yeah, the wire is creating the magnetic field. Yes. Yeah. So how did I know it here, right? So when we did this problem last time, through cross product, the magnetic field was out, and then it would be in. And what we said was to, just as a rule, to find the magnetic field easily, is to point your thumb in the direction of the electric, in the direction of the current, and your finger would be the direction of the magnetic field. So you're using your right hand for a couple things, right? Cross products and determining B field. So that's the direction of the force. Next, I'm going to, right? So next thing, I'm going to ask the magnetic force between two wires. The force between two current carrying wires. In this case, I just have one wire and then a charge moving parallel to it. By the way, if the charge starts to move leftward, in what direction would the force be? It would be the opposite direction, so up, yeah, it would be repelled. So, magnetic force between two current carrying wires. When I say wires, obviously they have a current. If they don't have a current, there would be no magnetic force. Okay? So here is a wire. This is wire 1. Let me call this one here I1. The current of this wire is I1. Okay? And let's say the second wire is here. And if we carry current I2. Okay. So the question is, first of all, in what direction is the force? The force on 2 due to 1. The force that wire 1 applies on wire 2. Is it going to be attractive or repulsive? It's, well, look at the positive charge. If you just had one charge moving to the right, what was the force? It was attractive. Well, what's a current? It's just a collection of charges moving to the right. Positive charges moving to the right. So it's going to be attractive. Every charge is going to feel a force downward, right? Remember, you got lots of pluses here, and all of these pluses are moving to the right. You got a string of them, not just one. So every little bit feels a force. Okay? So here is a little chunk here, ds, and there is a charge dq here. So the force on that little dq, df, I know the direction already. It's downward. And the amount of force is going to be dq times the velocity or the speed of that charge times the magnetic field. It's this. QVB, but instead of Q, it's going to be dq. We don't have one charge, it's just a collection of them, each of them is dq. Okay. Their velocity is, or their speed is ds dt. Is how quickly they travel around here, it's ds dt. So, we got df going to be dq times ds dt times b. So let's make dq divided by dt. So we have dq over dt times b times ds. That's df. Now what's dq dt?
Current.
Current, which one? Two currents. I1 and I2. Yes. We're talking about this dq is on this wire, so it is I2. This is I2. So you get df is going to be I2 times b times ds. So f, I need to integrate. Right? So let's say the wire, this wire has length L. Let's say the wire has a total, I mean, it has to be an infinite wire for the equation to work, but let's say it's a long enough wire where L is very long. L is long. So what does this become after you integrate?
Negative L over 212.
L over 2.
Negative 212. Oh, no.
So what does it become?
Yeah,
I
IL.
times the length. The integral of ds. What's the sum of all the ds's?
L.
L. So it is I2 times b times L. Now let's explicitly write b. I have I2 times b times L. Let's say the distance between the two wires is d. What's the magnetic field? Who is producing this magnetic field?
I1.
Wire 1, yeah, I1. Right? Wire 1 produces the field. Who feeds the field? Wire 2.
Back to
So, what's the magnetic field?
not I1, I2.
U naught, where is that? Yeah, over there, right?
Infinite order.
This one. U naught. I1 over 2 pi. And how far are the two wires apart? D, right? Not A. Over there we call it A, here I call it D. Let's clean this up. U naught, I1 times I2 times L over 2 pi times D. This is the force between the two ions, yeah.
So would the equation be reversed if we're thinking about the field being exerted on I2?
By Newton's third law, they would be equal, right?
Yeah.
Yeah. And if look at this. Oh, I2. It would be just I1 times I2 or I2 times I1. It's going to be exactly the same. And if wire 1 is pulling down on wire 2 would be pulling up on wire 1. So they're attracted to each other. Yeah.
Is the amount they pull on each other equal?
Equal.
Okay.
It would be exactly this. Yeah.
Would it be unequal if there's like different amounts of charge on each wire? Or
They would be equal.
when would it not be equal?
Newton's third law, at least for now, is correct. Yeah.
If there's a difference, materials, would it be different?
Newton's third law says you apply force on male, apply exactly the same force on you. It's equal and opposite. Yeah.
So the I1 is pulling on I2, but do the charges inside of I1 pull on each other?
The charge is, it's a neutral wire, so there are equal amount of pluses and minuses. Yeah. Yes, and then, yeah.
So for the B that you're using that you made yellow,
Mhm.
so you use the B from I1.
I know.
But on the top is when it's DQVB,
Yeah.
is that supposed to represent, like I guess for I2. So it's I2, but then the B is from I1.
Yeah. Yeah. So this one generates the field. It's felt by these. And then if you want to reverse it, this one generates a field down here, and then this wire over here.
The left side is forces on I2, and the right side is I0.
Yeah, so this is the force that charge one, that wire 1 applies on wire 2. Okay. So we're going to do a current loop now. And before I do a current loop, I need to review some cross products again. This one will have a good amount of cross products, so please follow with me. Okay. Yeah.
The right side is by one variables. How come you change EQ over to the I2 instead of I1?
What do you mean by I1 variable?
Like, if the right side, the magnetic field, is representative of I first current, then how come?
Yeah, what's the first current?
Then how come, on the second line, the DQ over utility, how come you, simplified it to I2?
Oh, okay. So let's start here. DF, right? So it's DQVB, right? Who is moving? Where is DQ at?
I1.
No. It's on I2. DQ is on I2. And who is moving with velocity V?
I2?
Yeah, DQ. Yeah, and who is generating the V?
I1.
I1. Yeah.
Okay, okay.
Yeah. So, all right. Let's please pay attention to this. I need your strong attention. So, here's a circle of radius r. Okay? Let's say the circle has radius r. And let's say here is the x-axis. Here is the y-axis. X and y. Okay? Where is the r hat direction? So if I'm here, let's say this is angle theta or phi. Let me call it theta. In what direction? Where is the I direction? The r hat direction. If I'm here, it's the radial direction. Points radially outward, right? Okay. So this is r hat. Okay. How much is r hat? How does r hat relate to I hat and j hat? That's the vector r, but little r hat is going to be cosine of cosine of phi I hat plus sine of phi j hat. We have done this one. So that's the, what's the magnitude of r hat? You should not hesitate.
One over
Yes,
square.
it's a unit vector, right? Has to have magnitude 1. Look at the magnitude. To find the magnitude, you do cosine squared plus sine squared, which is 1, right? And then square root. Square root of 1 would be also. Okay. So that's r hat. Now, in what direction is z hat? Or I'm sorry, the z direction, k hat. It's towards you, right? This is if this is x, this is y. The z axis is coming out. So the k hat direction is up. Okay. How about in polar or cylindrical coordinates? Phi hat. Yeah. In what direction is it? Circular, right? It's in the tangential direction. There are two ways to be tangent. There is the clockwise and then there is the counterclockwise. Which one is usually chosen?
Counter.
The counterclockwise, yeah, in the direction of increasing phi. So d phi, I'm sorry, not d phi, phi hat is this one. Okay, so that's phi hat. Okay? And I'm doing this because we're going to need it in a second. Yeah.
Are the theta and bicycles really similar?
The theta and the phi,
Oh, they just look the same on.
they're both phi.
Okay. Oh, okay. Got it.
Yeah, some books use phi, some books use theta. I'm just going with phi. Okay, so those are the directions, right? R hat is the radial direction, it's always radially outward, and phi is in the tangential direction going counterclockwise. Okay, that's phi hat. K hat is again in what direction?
Towards us.
Towards you. Okay. So let me ask you the following question. What is phi hat or r hat cross phi hat? What's their cross product? You like that? Yeah, it points that way, right? So the cross product of two unit vectors is also a unit vector, and it would point outside. Yeah. So it is this way, right? How do you do this again? Direction of r, curl your fingers toward phi, and you get that. Okay, so k hat. Next, I'm going to ask, what's the cross product of phi hat crossed with k hat? Phi hat cross k hat. R hat? Yeah, so here is, okay, so here is phi hat, here is k hat. What's their cross product? Yeah, it is r hat. Yeah. Your fingers from phi hat towards k hat. K hat, this way, towards r hat. It's in the r hat direction. Okay. So this is in the r hat direction. Which one we didn't do? Yeah, so k hat cross r hat is going to be what?
Phi hat.
Huh? Phi hat. Yes, it is phi hat. So k hat is out. K hat is out. I need to do cross product with r hat, so I get phi hat. Right? If you're in count 3, you should have done this a while ago or at some point. I don't remember. Okay, so that's that. Okay, I'm going to now talk about, and also, one more thing. One more thing. This one. I'm going to redraw my circle again. Let's say this is d phi, and this is ds. Here is ds. This is r, and this is d phi. So what's the relationship between ds and d phi? Just the magnitude. Good. R d phi. In what direction now is ds? tangent, so, yeah, phi hat. That's that. So,
How did you know the direction of that? You were given like she has an angle on a two. How did you get
by choice, we choose phi hat to be tangent and in the counterclockwise direction.
So is that phi hat and then that phi hat in the circle? Are they the same?
Which circle? This circle?
No, no, just that.
This one?
Yeah.
Yeah, this is phi hat.
No, but the one below, is that
This
phi
phi
hat?
is just the angle.
So they're different phis.
Yeah, this one is a unit vector in the tangential direction. This one denotes the angle.
Okay. So there would be no problem if I could say that instead.
Yeah.
Okay, cool.
Yeah.
Thank you.
Okay. So usually we just like to. I know we're used to like x and then I hat. Usually people like x and x hat, y and y hat. So it's just a choice of what. All right. So that's that. Now we're ready to go to Ampere's law. I'm sorry.
For the directions of phi hat, is phi hat always perpendicular to the point?
Yes. Perpendicular to r hat.
Or perpendicular to r hat?
Yes.
So, for ds, should it be like s? It's not in phi hat, like
It is. ds is tangent to the circle in the counterclockwise direction. So.
always staying tangent,
Yeah.
so it's not curved. Never mind. Yeah.
I'm going to now. Let me get my colors here. Okay. So current tube. Magnetic field. So imagine you have a current loop. The current of the loop is I, and the radius of the loop is R. Okay? The radius of the loop is capital R, and the current is I. So here is the loop. I'm pretending to draw in 3 dimensions. Yeah. So this is the loop. This is the z-axis. This is our y-axis. And this is our x-axis, right? That's the x-axis. And we have a current on the loop, and the current is on the loop. So it's going counterclockwise in this case. I'm just going to choose it. The current could go clockwise or counterclockwise. I'll just choose one that is going counterclockwise. That's the current. And our goal is to find the magnetic field, the distance z above the center of the loop. So we're on the axis of the loop, the distance z above it. So, how did I maybe go there? Just wanted to be consistent with the point. So let me say this vector. What's this vector here? The red vector.
Z.
Z, it has magnitude Z, right? It's a distance Z above the center. And what direction?
Z.
Yeah, Z hat or K hat, right? The Z direction, so K hat. So this vector is in that direction. Right. So now let's look at the current. Let's take a small segment of the current. So let's say here. Here is the current. Current runs tangent, right? That's ds. So this is the current. Everywhere it's tangent to the circle. And this is theta or phi. So what's ds in terms of the radius of the loop?
R
R what?
RDV.
Yeah, R dv. And then the direction direction is in the phi hat direction. So to apply Biot-Savart law, I have ds, I need r. R is a vector that starts at ds and ends at the point where you're finding the magnetic field. It starts where? ds and ends at the point P, right? Where we want to find the magnetic field. We would like to find the magnetic field at that point, see? So I'm going to draw my vector R now. Here's the vector R. It starts here and ends here. This is the vector R. That's the vector. We already found ds. I need to find R. Look at the purple vector, this one, plus the yellow vector. So if you add this vector to this vector, what do you get? You get the red vector, yeah. So this vector takes you from here to here, this vector takes you from here to here. Well, notice C does the same thing, takes you from here straight to here. So notice that C K hat is equal to this purple vector. What's the purple vector?
R squared. I mean R.
It has magnitude r because it starts at the center of the circle and ends in the circumference. But how big? I mean, in what direction is that?
R
It's radially outward. It's r hat. Right? This vector. It's r hat. This one is p. The one the tangent. Yeah. Okay. Plus what? Plus what?
plus Z. I mean
Oh, we said this vector plus something equals to this one.
R vector.
So plus the r vector, yes. Therefore, the r vector is simply equal to c k hat minus r times r hat. R hat is radially outward. This is r hat. Yeah.
So then that little r, that's purple, and the little r, that's yellow. Those are not the same, right?
This one?
Yeah.
That's the radius of the circle.
No, I mean like the little r that's purple, that's the
Oh, r hat.
Yeah,
Oh.
that one, and the other, the yellow r.
They're not the same. Yeah.
Okay, and the theta in the circle, and then the theta under the hat symbol are also not the same.
Okay.
Okay.
Phi hat is a unit vector. Tangent. Phi it just measures the angle from the x-axis. Yeah, and then r hat is a unit vector that points radially out. So this is the flat side. That one is basically we kind of tried to orient it this way.
Yeah, like looking at it from a bird's
Yeah,
eye.
yeah, yeah. Yeah. How about now the magnitude of this vector r? What's the magnitude?
R squared plus Z squared.
Okay, so d squared plus r squared to the 1/2. That means r cubed would be what? Why do I want r cubed?
Because you are going to use vector.
The Biot-Savart law has the r cubed on the bottom. So I'm just getting it ready. Okay. Now we need to do the cross product. The cross product. We need to do ds cross with r. Okay, cross with r. So what's ds? Okay, yeah, there. R, dp, and then p hat. And then cross product, I would use a different color. This is not x, this is cross product. R.
ZK.
This is like this. Yeah. All right, we're ready now for our cross products. The first cross product will involve phi hat cross k hat. Phi hat cross k hat is R hat. Phi hat cross K hat is R hat. So the first one, you have phi hat cross K hat is R hat, so I'll put R hat. And then don't forget these, R, D theta, and Z. So Z, R, D theta. Oh, I'm sorry, D P theta. Anything I forgot? Seems okay. The second cross product is this one. Phi hat crossed with R hat. Yeah. So, okay, I asked phi hat crossed with R hat. I heard negative K hat. Yes. Because R hat cross phi hat is positive K hat. So if you reverse the cross product, you get a minus sign, right? Remember the rule or one of the identities A cross B is equal to minus B cross A, right? Cross products. So again, I want you to hear it. What is phi hat cross R hat?
K hat.
Negative K hat. Negative K hat. But I have a minus sign. So what does it become?
Positive K hat.
Plus K. So plus K hat. And now let's multiply R, that's R squared dp. That's this cross product. Right. What we have left is the integration part. It's going to be a simple integral. A lot of stuff will cancel, become zero. So that's so dv yes. This is R cubed. Notice R cubed or R is a constant, right? Because Z is a fixed point and then the radius of the circle is also constant. So this is a constant. When we're going to integrate, that stays outside. So I'm going to write this. U naught I over 4 pi. My R cubed is going to be here. Z squared plus R squared to the power 3 halves. And then this cross product. ds cross r. This is ds cross r. So I'm going to write that. C r dp r hat plus r squared dp k. That's dp. Looks like a lot of stuff, but again, much of it is going to cancel. It's going to be zero. Now, to get b, you need to integrate dt. I have two terms. I have this one and this one. Those are the two that I'm going to use. So I'm going to write this one first. I'm going to ignore the stuff in the outside. This is constant, and I can add it later. Just multiply the integral. I'm just going to do the stuff inside the bracket. So this one, Z, R, dp, and then R